When working with rational functions, you're going to work with a function that looks like this. F of x is equal to p of x over q of x. And when you graph a function like this, it's going to take on the appearance of something like this figure. So you have two smooth curves, and these curves, they approach a vertical line called a vertical asymptote, which is the line that they're going to get very, very close to but never cross. And they're also going to approach a horizontal asymptote, which is a horizontal line that the graph gets very close to but doesn't cross as well. So in order to graph rational functions, we're going to do these 5 steps. The first of which is to find all of the intercepts for your given function. The second is to find the vertical asymptotes. So there may be just one, there may be 2, but we have to find all of them, and that'll help you graph. The third is to determine where the horizontal asymptote occurs. The fourth is to find a table of values, and that'll help fill in the gaps and help you graph. And the last step is to draw a smooth curve through all of the values that you found. So first, let's work a few rational functions. We're going to find the value of them and determine their domains. For our first problem, we're asked if g of x equals x plus 3 over x plus 1, we need to find the value given these values for x. So let's jump right in and find g of 0. So we plug in 0 for x, and we get 0 plus 3 is 3, and 0 plus 1 is 1. So 3 over 1 is 3. For g of negative 3, we plug in negative 3 for x, negative 3 plus 3 is 0, and negative 3 plus 1 is negative 2. So we have 0 over negative 2, which is 0. For g of 3, we plug in 3 for x, 3 plus 3 is 6, and then 3 plus 1 is 4, so 6 over 4 can be simplified to 3 over 2. Now g of negative 1, let's plug this in. Negative 1 plus 3 is 2, and negative 1 plus 1 is 0. So we have 2 over 0. So this is a special case. We have a denominator of 0, and we know that that means that our function is undefined where our x value is negative 1. So this answer here is undefined. So that's important to look out for what values will make the denominator in our given function 0 and therefore undefined. So one last value to find, if x equals 1, 1 plus 3 is 4, over 1 plus 1 is 2, so 4 over 2 gives us 2. Okay, our second problem here asks us to state the domain for a couple functions. Our first function is f of x equals x minus 3 over x minus 1. So going back to thinking about what values for x will make the denominator 0 and therefore this function undefined, we can look and see that if x equals 1, then we have 1 minus 1 and our denominator is 0. Therefore this function is undefined where x equals 1. So we can write our domain as this. X is all values such that x does not equal 1. Simple as that. So our second function here, h of t equals t minus 4 over t squared minus 16, will do the same thing. Look to see if we can figure out what value for t will make the denominator 0 and therefore undefined. So what value squared equals 16? Because if we subtract 16 from that, we need to get 0. So we know that 4 squared equals 16. So t equals 4, that would be a value where the function is undefined. But we're not finished yet. We also have to remember that when you square a negative number, you get a positive number. So if we were to square negative 4, we'd also get 16. So t equaling 4 or negative 4 would make the denominator in this function 0. So our domain we can write as t is all numbers such that t does not equal 4 and t does not equal negative 4. So it's important to make sure that we get all the values for our variable that would make that function undefined. So now let's move on and we'll graph a function. Let's graph y equals x minus 3 over x plus 2. So our first step when we graph this rational function, let's find the intercepts. And for the x-intercept, we know that that occurs when y equals 0. So we can set our function equal to 0 and then solve for x. So we have 0 equals x minus 3 over x plus 2. Now to simplify this, we can multiply both sides by this quantity x plus 2. We know that on the right side, if we multiply x plus 2 times 0, we still have 0. And then multiplying this side by that quantity, it cancels out, so we're left with x minus 3. Then we solve for x, and we get x equals 3. So our x-intercept occurs where x equals 3. Now let's find our y-intercept. This occurs where x is 0. So we plug in 0 into our function. 0 minus 3 is negative 3, and 0 plus 2 is 2. So our y-intercept occurs at negative 3 over 2. The second important thing that we need to find before we graph our function are the asymptotes. So a vertical asymptote occurs where our function is undefined, so where our denominator is 0. So looking at this, we can see that if we plug in the value of negative 2 for x, we get a value of 0 in that denominator, making our function undefined. So we can say that our vertical asymptote occurs when x equals negative 2. Now for horizontal asymptotes, we're going to look at our polynomials in our function and pay attention to their degrees. So if you look at the degrees here, we see that we have equal degrees. Each each degree on this first term of the polynomials is 1, and they equal. And when we have a case like that, then our horizontal asymptote is equal to the line of y equals a over b. Now a is the leading coefficient of our first term in the top polynomial, and b is the leading coefficient in the bottom polynomial. So we see that our coefficients here are each 1. So y is equal to 1 over 1. Therefore, our horizontal asymptote occurs where y equals 1. Now, if we were to be dealing with a function that has differing degrees when we compare our polynomials, then that means that if the degree in the top polynomial is less than the degree in the bottom polynomial, then your horizontal asymptote will be the x-axis. And we'll talk about that, take a look at that in our next example. But for now, our horizontal asymptote for this function here, where the degrees are equal, is y equals 1. So now let's fill in our table of values with some of the information that we just found. I plugged in a few other points to help us graph, but let's also add, let's see, we've got our x-intercept, which is where y is 0, so we can put that down here, is at 3, 0 is our x-intercept. Our y-intercept occurs where x equals 0, so we can plug in negative 3 over 2 here at 0, negative 3 over 2, which is our y-intercept. And then also for the value of negative 2, that was our vertical asymptote, and we know this is where our function is undefined. So I think we have enough information. We've got some good points here. Let's plot them on our graph and see what we get. So we have negative 7, 2. We can add that dot here. We have negative 3, 6 here. Then at negative 2, this is where it's undefined, where x equals negative 2. So we know that that is our vertical asymptote. And this is the vertical line that our function will get extremely close to, but it will never cross it. So this is where x equals negative 2. Moving on at negative 1, negative 4, we'll plot that here. Then our y-intercept at 0 and negative 3/2. So we have 0, negative 3/2 goes here. And then our last point from our table is our x-intercept at 3, 0. Okay, so knowing the general shape of our rational function, Oh, you know what? We have one more thing we need to plot. We need to add our horizontal asymptote. So at y equals 1, we can say this is our horizontal asymptote, which is, again, the horizontal line, which our function will get very close to but not cross. So that helps us even more to shape our graph. So we can draw a smooth curve through our points and say that this is approximately the graph of our function y equals x minus 3 over x plus 2. So let's do one final example that deals with two polynomials with differing degrees. Let's graph y equals x over x squared minus 4. So first off, let's find our intercepts. For our x-intercept, that's where y equals 0. If you calculate that out, we get an x-intercept of x equals 0. For the y-intercept, we find it where x equals 0, and we find out that that occurs at 0 as well. So our x-intercept and our y-intercept are going to occur right at the origin at 0, 0. Now for our asymptotes, our vertical asymptote occurs when we have a value of x that makes this function undefined. So if we look at our denominator here, we have x squared minus 4. We know if we plug the value for 2 in for x, we get a value of 0 because 2 squared is 4 minus 4 is 0. We could also plug in negative 2 for x and get 0 as well. So our vertical asymptote, actually we now have two vertical asymptotes at x equals 2 and x equals negative 2. Now our horizontal asymptote, this is where we need to pay attention to the degrees of our polynomials. So if we look at our top polynomial, the degree here is 1, and the degree of the bottom polynomial is 2. Now when the degree in the top is less than the degree of the polynomial in the bottom of your fraction here, then we need to determine that the horizontal asymptote is going to be the x-axis. So that occurs where y equals 0. So now we can use this information here and plot those values on our graph. So we've already added our x-intercept and our y-intercept, which occur both at 0, 0. Our asymptotes, I'll draw in our vertical asymptotes here. The first one is where x equals negative 2. And the second is where x equals positive 2. Our horizontal asymptote is already drawn because that's our x-axis. So if you were to find a table of values and plot your points, you would end up with a graph that looks something similar to this. Crosses at 0, 0. All of our curves get very close to our asymptotes but never cross. So here is what the graph looks like for our function y equals x over x squared minus 4. So when you're graphing rational functions, make sure that you're finding the intercepts and the asymptotes, and then maybe figure out a table of values to help you graph, and it'll make the process much simpler.